Hello, Mr. Eric, Mr. Ryan, alright? Okay, so let's visit the binary trees. Okay, binary trees. Okay, we talk about binary trees lots of times. Binary trees. So in one sentence, what's binary trees?
A binary tree is a tree with numbers and the left 2 kids.
Okay.
And the left of the tree, the root must be smaller than it, and then
No, that's binary search tree. Okay, you're talking a little bit more forward.
Most 2.
Okay, so I pick the keywords. Okay, so 2, right? Binary 2, right? Yeah, and the numbers. It actually the nodes does not necessarily be numbers. It could be strings, any type of data. So binary tree is like a data structure. Okay, it's a tree. And what are trees? Trees are directed acyclic graph. Okay, yeah. Directed means that it's actually doesn't have a direction, but we call it directed acyclic graph because usually we want to give a list trees, binary trees, whatever, that we can only visit the kids from the parent. So it's always one direction. Yeah, we cannot go in a reverse order. Yeah, unless you store the parents. That's totally the other story. A cycle, it doesn't have a cycles. If it has cycle, we call it graph. Okay, it doesn't have cycles. Graph. Okay, the trees are graph. And the binary tree, particularly, like a parent can only have 2 kids at most. It can have 1 kid, it can have 2 kids, but it cannot have more than that. If it doesn't have any kids, we call it leaf. Okay. If the parent, if a node doesn't have a parent, what do we call it?
Forest.
Root. Yeah, the root doesn't have a parent. Okay. So for this binary tree, if we remove one edge, what will happen?
It will separate and be a forest.
Well done. You will separate into two trees, two trees. Okay, one tree will be the subtree of the another one, of the entire tree. Okay. So we call it. Let's multiply the sum of these two, right? For example, if I remove this edge, so that will become a 4. Okay. So what's the sum of these remaining tree?
It's 11.
11. Then let's times the sum with 44. Okay, and then how about if I remove this edge?
There'll be 10 times 5 is 50.
Okay, so this is the maximum. Okay, if we keep
So
removing,
far.
because look, there are how many choice can we do? Can we separate? How many edges? If we cut like that, 1, 4, 3, 4. So if we cut one edges, they'll become 2. Okay. So we want to find out to maximize the split sum. Okay. Okay. We want to maximize the split sum. How are we doing it? How can we do it? I mean,
we can do it.
so look at this sum.
DAG.
Maximum sum. Okay. So if we remove it, right? So first of all, if we remove it, we get 2 trees, right? Let's focus about the subtree, right? Because look, if I remove this edge, this is a subtree, right? If we know the subtree, and if we know the subtree, let's say if the total sum is t, okay? Right? Eric, the total sum is t. We can do this with depth search or breadth search, in one go, right? Yeah, remember? If this t, and then if I tell you the sum of these is, or the subtree is, let's say, t prime. Okay?
T prime.
Okay, what's the subtree of the remaining? I just actually written there. Sorry? If the sum of all, everything is t, and if the subtree, if these subtree, t prime, and then what's the remaining sum? Come on, it's very obvious.
1.
Huh? No. Sorry.
T minus T primes.
T minus T prime. Yeah, I was just written there and then rub it out. And then, yeah, you see? So
smart.
Yeah. So look, the maximum sum. We want the maximum this, yeah? T minus T prime times T prime. Right? T minus T prime is this bit. Yeah. If we remove this bit, T prime is this bit. Okay, so it's actually T minus T prime is this bit times T. Okay? So So we want to maximize. We want to maximize this. Maximize t minus t prime times t. Okay? No, times t prime. Okay, sorry, times t prime. Okay?
Yeah.
Yeah. So in order to get this t sum, we can do this default search or breadth search. It's easy. Yeah. Let's quickly write it. It's easy. We've written this before. Right? Define root. If not root, return what?
That pen is bad because you
Nothing.
The sum will be what? If
Nothing.
nothing. What's nothing in sum?
0.
0. Yes, well done. 0.
Damn.
Okay. If not root, okay, it's wet. Return 0. Okay.
If you write on wet stuff, it will.
Then return what? Root of value plus the left bit. What's left bit? Come on, it's easy. Recursion. It's easy.
Appends.
Root of value plus the left bit. Sum what? And then plus sum what? Recursion. Come on. I want to calculate the sum of the entire tree. And then if the root is empty, I return 0.
Some 0 and some 1.
And root of value plus the left bit plus the right bit. Come on, this is the easy part. You can figure it out. Huh?
Some left plus some
Root of what?
left plus some root of right.
Yeah, easy. This is easy. Yeah. Look at that with recursion. Yeah, recursion. The sum of the entire tree equals what? Look, the sum of the entire tree equals 1 plus the sum of the left tree and the sum of the right tree, which is we already know, yeah? This is the recursion, yeah? Yeah? Got it? Make sense? This is easy. So if we perform this default search, recursive default search once, that takes O(n) time if there are n nodes, right? Then we get this t, right? Right? Yeah? So then we can do another default search. And then in the meantime, yeah, we can, because this is the sum of every subtree, right? Basically, it's the sum of every subtree. This is the same as we remove one edge, right? So we try every possibility of removing each edges. So once we remove one edges, that will be a sum. Yeah, that will be a partial sum of another subtree, right? So we can do this. So we can do another default search, okay? Default search. And I possibly need okay, never mind.
Just wait for dry.
Wait, give me 1 second.
Tissue.
So guys, let's have a little chatty.
Okay, sit down, please. Okay, so we can do another default search, okay? Default search root. So at the meantime, we have this answer at the beginning. Let's say max infinity, the negative big, the most smallest number we can think of is the minus negative, okay?
Minus negative.
Okay, so this part is quite the same, yeah? If not root, return a 0. Actually, we just copy over, right? And we can have this. So the left bit, so what? The current will be equals root of value plus default search root of left plus default search root of right. Okay, so once we have these values, okay, so this is the subset sum, right? So we can say, okay, answer equals max answer. Yeah, we want to get the maximum, right? But now we know the total sum, right? So before we call this function, we have a total. Let's say just call it t equals sum rule, right? So we use this function to get the sum first, and then t times t minus current times current, right? Yeah, that's what we said. Yeah, right? Now we are at this point. We know that's the sum of this subtree, right? Yeah. And then t is the total sum minus the current subtree is the remaining tree, the sum of the another tree and times itself, okay? And then return This is the same. Return current. Okay. Yeah. So we do this once. We do this twice. Do another. So look, these two functions is quite similar, right? Except that this function by itself is returns these two functions is actually the same, returning the sum of the current tree. The only difference is that we have added this plugin here, plug in this value to obtain the max split sum. But it needs this t first, right? We don't have this value first, right? So that's why I need to call this function first to get this t, right? Because the sum of a total tree doesn't change, right? Am I right? Yeah? We given this binary tree, you know the sum already, right? It's never changing, right? It's not changing. But we can't call this function directly because t we haven't known, right? We need to get it here, right? This is on. This is on. Overall, what's the time complexity overall? What's the time complexity? Sorry? If I perform this on and this is on, what's added together?
O2n.
And what's O2n?
O-n.
You write it down. We drop the constant on, okay? Yeah? Okay, so another way would be similar to this. Instead of doing this, we can store all the values, all the subset sum in a set, right? In a set, which is unique, yeah, in a set, and then we can go through the set later, right? So I'm just quickly writing, yeah. This is another way, yeah.
Slice in half.
So we can go. So look, we have this sum. Okay, let's say sum. Okay, sum equals a set, right? What's a set? What's set?
Set is like is better than the list thing, because if you look up for something in the set it's O1, but in list is O-n.
Yeah. Okay, there is no one better than the other. It's just for different purposes. The set stores the unique numbers only. Yeah. It's a unique. It only stores the unique elements. Alright. So let's say we have empty set and then we have this depth search first, yeah? So this is the simple, yeah? If not root, return 0, yeah?
Yeah,
Easy.
if not root, return 0.
And then left bit equals depth search, the sum of the left tree, the sum of the right tree equals depth search root the right. Yeah, we're recursively calling this function to attempt the sum for the left tree and right tree. Okay, then we can do this sum dot add. We add the left tree. Then look, any tree, yeah, and look. So 1, 2, 3, 4, 5, 6, 7. So look, if calling this root here, and I will call the left, which is the tree of these, the sum will be 2, 4, 5. 2 plus 4 plus 5, 11. And I added the 11 to the set, okay? And the right tree, what's the sum of the right tree? It's 3 plus 6 plus 7 is 16. And I put a 16 in the set, right? Sum dot add. Right? And also the current will be what? So I also need to add what? Sum dot add. Left plus right plus root of value, right? And then I need to return this value, yeah? return this bit. So this total, okay? Let's save. We can save this in a value total. Okay? Left plus right plus root of value. Okay? Look, yeah. So once I done this, what should I do next? Once I done this, what should I do next?
We run it.
So look, if I do this, I add the set adds the possible left tree sum, the right tree sum, and then all overall, right? So I need to go through the set, right? And I know this. The total, right? So I can do this. Total equals depth search root.
For I.
Yeah, and then I go through the I in this set. Yeah, some set. Okay. And then answer will be the minimum again. Infinity, yeah? Infinity. Answer equals max answer t minus I, right? Times I, right? Yeah, this is the same. So we do this. We first of all perform this default search, and then we collecting all the sums in the set. Yeah. So the set contains all the possible subset sums because we're adding the left sum, the right sum, and then the current overall sum, right? And then we go through the set again. T, yeah, we already go this. T also, okay, so this function return does two purposes. First of all is to collect the values, the possible sums in the set. The second value, second purpose is to return the sum of the overall tree, of the current tree, right? What did Daddy just say?
Is to sum the overall things of a tree.
And then what's the second purpose?
The second purpose is to add the overall of a.
What's this? Sorry?
Oh no. Sum add the left.
Huh? What's the two purpose of this function? Come on, if you read this function.
Okay, the search is not really to return 0.
Yeah, I know. I can read the code. What I mean is, what's the purpose of this function? What does it do? Come on.
It's
What's this? What does it do? There are two things here. Here, first thing, and here's two things. Okay. So what does this do? What does it? I'm saying that what's the purpose of this function? Come on.
Sum add left.
Yeah, I know. What's
adding
what?
The
Yeah.
left bit.
And some do add right is adding the right part.
Yeah, into.
The set.
What's this?
It's timesing
And
the root.
What's this?
left plus right plus root dot value is the
Entire tree.
yeah,
And I put it in the set
in
as
the
well.
set. And the second part you just did is return. It's return the
Answer.
The value of the sum of the current tree. Yeah.
uh,
Okay, that's two purposes. Yeah, I know you understand. Yeah. Okay. But you need to work out on your presentation skill to make it clear, to demonstrate that. Okay, to explain it well. Okay, and then by going through this the subset, the possible sums in a set, then we can calculate the maximum of the space sum, right? Yeah. Look, t minus I times I. What's this mean? Come on. T minus.
T minus I times I.
Yeah. What's t minus? Can you explain to me what's this? T minus I times I.
It's the t which minus I and times I.
Yeah. What does it mean?
It means
So you times
So what's t?
T is the tree. The tree.
What's the t here? T equals default search root. What's t?
t is the deficit root.
The tree.
What does it return? What's it mean? What does it? You just say here. Then t equals default search root. So what's this meaning?
The whole tree.
The whole tree. What of the whole tree? What are we doing here? What are the whole tree? So what's the value? If I call t equals dfs root, root is here, points to here. What's the value of it? What's the value? What's this t?
T is the value.
Is the what values? Come on. What's it return? It's a value. Huh?
Root.
It's a root here. Root is 1. So what I call t equals default search root. And what does t equal?
T equals 1, 2.
1 what 2? What are we doing here?
1, 2, 3, 4, 5, 6, 7.
Yeah, what are we doing with the numbers?
4, 3, 1, 2. Wait, 1.
What's this function return? Left plus right plus root of value. Root of value is 1. Left is
1,
the
2,
root of left is
1,
this
2,
bit.
4, 3, 5, 6, 7.
Yes. Okay, you're still not getting it. T equals default search root. If this is the tree and root is pointing to here, this is the root. And what does it return? If you say okay, it's return left plus right plus root of value. So the left is dfs root of left here. Right is dfs root of right. Value is 1. So it equals 1 plus the left bit plus the right bit. So the left bit equals 2 plus the left bit plus the right bit. So it's recursion. So what's this function returns what? What does it return?
Left plus right plus root of
The the left thing
Tree.
is that
The left tree
that
plus the right
and
tree.
Yeah, I know the left tree plus the right tree. What plus? How do you plus the left tree and the plus tree? The numbers. What do we do with the numbers?
Add them all up together.
That's the one I want. I want. Add them together. That's the sum. Okay. T is the sum, so it's 1 plus 2 plus 3 plus 4 plus 5 plus 6. Yeah. So that's how much? 28. Right? Is it 28?
Wait. 2 plus 4 is 6. 6 plus 5 is 11. 11 plus.
Yeah. Okay.
11.
28. Okay. So T 28. The possible sum. Okay. So left bit is what? 2 plus 4. So what's in the sum? Sum is 4, 5, 6, 7. Yeah. And then what? 2 plus 4 plus 5. Yeah. What's that? 2 plus 4 plus 5 is 11.
11,
7 plus 3 plus 6 plus 7.
16.
16. And then all together is what? Is what? It's 28, right? Okay.
Yeah.
So I need to go through this number and then I try to do this. T minus I times I. Okay, coming back to this question. What's T minus I times I?
It's the sum minus.
This is the total sum. And the minus I is here. I is here. I is here in one of these. T minus I times I. What does it mean?
It means the total sum subtract the I there.
Yeah, what does I represent?
The left and right tree.
It's the sum of the left, right.
It's the sum of any subtree, right? Yeah. So remember, coming back to this question, we want to remove one edges and then split into two. If we remove this one edge, then this sum will be 2 plus 4 plus 5,
Which is
which is 11. And 28, I know 28, right? So what's the sum of this bit?
It must be 17.
Well done. Yeah, the total is 28,
And
never
then
change. This is 11, right? So the other part is 28 minus 11. And then the product is what? T minus I times I. That's it. Got it? Make sense? Yeah, well done. Okay, that's it for today. Good job. Bye bye.